So adding a little bit of detail to our process diagram for seamless pipe and tube, we might expect to see normalized microstructures and possibly quenched and tempered microstructures. For double submerged arc pipe and tube, we could expect normalized and possibly thermomechanical controlled process microstructures. And then for our ERW pipe, we could expect possibly all three: normalized, TMCP, and quenched and tempered. There are other processes that can affect the microstructure, either desired or undesired. One that's typically undesired is during normalizing or annealing of the pipe. Surface decarburization can occur. In the annealing furnace, if the pipe is held at high temperature for too long, the carbon can actually come out of the first few micrometers of the surface as a gas. And so with carbon lost, then the strength would be different. The material would have almost no perlite, and that's undesired. Localized processes, including welding, local annealing of welds, especially seam welds, and girth welding, can leave a weld fusion zone, a heat affected zone, and a normalized region around the weld. Other processes that deform the material and affect the strength are sheet flattening, coiling, straightening, leveling, and cold expanding. Now what these processes do is make a shape change or a little bit of plastic deformation that may actually be difficult to find in the microstructure, but can leave a large effect on the final strength and especially on the residual stress in the product. So we've talked about how processing affects microstructure, and now we need to talk about how orientation can affect microstructure. The direction in which you section and observe the microstructure of your line pipe steel can make a difference in the appearance and the evaluation of that microstructure. So this is the longitudinal direction up and down our line pipe, and if we section and look at the microstructure in the longitudinal direction, which is a typical direction to look at destructive micrographs, one feature that we'll notice quite often is banding. What am I calling banding? Banding are these regions of dark phase that are aligned to the left and right, indicating that as the steel was deformed into plate or strip, the regions of perlite were elongated, mostly in the longitudinal direction. Now, there can also be banding in the transverse direction, but it is not as common. So we could see banding this way as well, but it's not as common. Now, we'll almost never see banding in the surface, on the surface. Now, this is really important, this direction of observation, because this is going to be our only option for non-destructive evaluation of line pipe steels. So it's going to be important for us to think about and to consider how these directions will be different, because the two common directions for destructive analysis of microstructure and the two common directions that give the most representative and most information about the microstructure are longitudinal and followed by transverse. But our only option for non-destructive analysis of the line pipe steel is the surface, typically performed by a replica. And here I've brought in just a few different examples of three-dimensional microstructures, similar to the one we previously analyzed, where for all of these, on top you see the surface microstructure, kind of like what we would see if we take a replica of the surface. You see the longitudinal microstructure to the left and right, and then the transverse microstructure. So let's look at some of the observations we can make from these. I'm going to start with the lower right-hand corner. This one's interesting because you don't really see any banding in the longitudinal microstructure. So if we analyze each of these surfaces, each of these microstructures, we might actually get similar answers, really similar answers for the longitudinal, the transverse, and maybe even the surface replica. So that one would be a good one. That would be an interesting one to look at. Probably would follow the rules and be really good for our correlations. Similarly with low, a little bit less of the second phase, the dark phase, is the one in the lower left-hand corner, where we might expect to get similar answers from analyses of the longitudinal, the transverse, and even the surface microstructure, because they look pretty similar. Although the transverse has a little bit different etching response, we'll learn how to adjust our evaluation for the etching response a little bit. Now, if we look at a few of these other microstructures, we see bottom center, we see some banding going on here. Let me switch to a green highlighter. So sorry about that. We do see banding here and we don't see it here, but it still, to my eye, doesn't look like the surface analysis is going to be that much different from the longitudinal or the transverse directions. Similarly, for top center, there's banding in the longitudinal, banding in the transverse direction, and then the surface looks completely different, but maybe it's going to be similar in terms of quantitative analysis to the other orientations. So where we do see some really interesting differences are the upper right and upper left. So here's some banding in the longitudinal direction. Here's a little bit of banding in the transverse direction, and a little bit different etching contrast between the ferrite and pearlite that we would have to adjust our methods to. But it's really interesting here on the surface because of the different cuts. What's going on here is the dark area, you see these splotches of dark phase, a lot more dark phase, and then a region with a lot less dark phase. That's because of the angle at which we're intersecting those bands with the surface analysis. So how do we overcome this deficiency or this potential problem? Probably the best approach is going to be by evaluating multiple fields. Similarly, upper right-hand corner, we see some banding in the longitudinal direction, banding in the transverse direction, and we see these splotchy regions with a lot of the dark phase and then almost none of the dark phase. So again, we're going to have to probably, for a microstructure like this, we're going to have to analyze sufficient amount of images, a sufficient number of fields of the surface replica to make sure we're getting a statistically significant quantification of the second phase. In addition to having an effect on the amount of second phase evaluation, processing can also have an effect on grain size evaluation. Here we're going to look at thermomechanical controlled process pipe microstructures, and we'll start with the longitudinal microstructure we see here on the left. We see this banding again, but something else we notice is that some of the grains are elongated in the direction of rolling. So that can lead to a difference between the longitudinal direction destructive microstructure and the surface replicate. So when we look at the surface replicate on the right here, one thing we notice right off is that the second phase, the dark phase, isn't as distinct as it is in the destructive replicate. So that's going to be a little bit more of a challenge for our assessment methods. And then the grains, because of that effect of thermomechanical controlled processing on the elongation appearance of the grains, elongated appearance of the grains, we see a different appearance, and there's a different appearance possible for the grains on the surface. Here's another couple images of thermomechanical controlled process pipe where we are going to highlight the difference that we can see for the grain structure between the destructive longitudinal microstructure and the non-destructive surface replicate microstructure. Again, we see some of these elongated grains in the longitudinal direction, and here we don't see very much second phase. But when we look at the replicate microstructure, we see that some of the grains, a lot of the grains actually look larger on the surface, and then they seem to be dotted with very fine grains. So I believe this effect is due to something in thermomechanical control process that they call the forming of pancake-shaped grains. Those pancake-shaped grains and that plate-shaped orientation is going to look like an elongated grain in the longitudinal microstructure, but in the replicate microstructure, looking down on the surface, it's actually going to look more like looking down on the surface of a pancake. It's going to look enlarged in multiple dimensions.